Hello there, and welcome to the Sleepy Science Channel. Tonight, we step into the hidden world of trees, a world that surrounds us every day, yet remains full of secrets waiting to be discovered. At first glance, trees may seem still and silent, but beneath that calm surface, there is movement, communication, memory, and a kind of living connection that stretches across entire forests. Roots reach through the soil like unseen pathways. Leaves gather light with quiet precision. Signals pass between trunks and branches in ways that feel almost impossible, yet are very real. Some trees have stood for thousands of years, watching climates shift and civilizations rise and fall. Others form vast networks, sharing resources and responding to the world together, as if a forest were more like a single living system than a collection of individuals. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is settle in. Let your shoulders soften. Let your breathing slow, and allow your mind to drift as we explore the secret lives of trees together. Let's begin. Trees can communicate danger through the air and the soil. When insects begin chewing on leaves, many species do not simply endure the attack. They respond with chemistry. A damaged tree can release airborne compounds that drift outward and alert nearby plants. Those neighbors may begin producing bitter or toxic substances before the insects even reach them. Beneath the ground, another layer of messaging can unfold through roots and fungal partners. Signals can move through these buried connections, helping surrounding plants prepare for stress. This is not speech, and it is not thought in the human sense, but it is communication with real consequences. A forest may look still from the outside, yet inside it, information is constantly moving. Warning, response, defense, and survival all happen without a voice. Once you know this, a woodland no longer feels silent. It becomes a living network, filled with messages too subtle for us to hear. Some trees have lived since before the Great Pyramid was built. High in the mountains of western North America, ancient bristlecone pines have been growing for nearly 5,000 years. Their trunks are twisted by frost, drought, and wind, yet their living tissue keeps working in narrow strips beneath weathered bark. These trees were already old when Rome was young. They were rooted in place while empires rose, languages changed, and entire calendars were invented. Part of their secret is slowness. They grow in harsh places where few competitors survive, and their dense wood resists insects, decay, and damage. Instead of rushing upward, they conserve energy and endure. Some sections of a trunk may die, while another small ribbon stays alive for centuries. Standing beside one is almost like standing beside time itself. It reminds us that life does not always need speed or softness. Sometimes its greatest power is patience. Forests can make their own rain and shape distant weather. Large forests do more than receive rain. They help create it. Trees draw water from the soil, lift it through their trunks, and release it from their leaves as vapor. Across millions of trees, this becomes an immense invisible river rising into the air. In the Amazon, moisture released by the forest can feed clouds that travel far beyond the canopy. Some of that water falls again as rain, keeping the system alive. Some moves across regions and helps influence weather elsewhere. Forests also release tiny particles that can help water droplets form in clouds. So a tree is not just a living object beneath the sky. It is part of the sky's machinery. Remove enough trees and the pattern can weaken. Protect them, and whole landscapes can remain wetter cooler, and more stable than they would be without them. A tree can feed its neighbors through underground fungal networks. Beneath the forest floor, roots often connect with fungi in partnerships that are far older than human civilization. The fungi thread through the soil and gather minerals that roots cannot easily reach. In return, trees provide sugars made from sunlight. In some forests, this exchange can link many plants into a shared underground economy. A shaded seedling may receive carbon from larger trees. A stressed tree may gain support from nearby partners. Researchers have traced movement of nutrients between individuals, revealing that forests can be more cooperative than they appear. This does not mean every tree is kindly helping every other one. Competition still matters, and the network can serve fungi as much as trees. But the discovery changes the way a forest feels. Under every footstep, there may be trade, negotiation, and survival passing through threads finer than hair. Trees breathe out much of the oxygen we depend on. Every green leaf is a small solar workshop. Inside it, chlorophyll captures sunlight and uses that energy to split water and transform carbon dioxide into sugar. Oxygen is released as a byproduct, and that byproduct changed the history of Earth. Long before forests existed, early photosynthetic life began filling the atmosphere with oxygen. Later, trees became part of that great planetary system, helping maintain the air that animals breathe. A single tree does not make the atmosphere by itself, and ocean plankton play an enormous role too. But forests still matter deeply. They store carbon, cool landscapes, and feed oxygen back into the living cycle. Each breath you take belongs to a story that reaches through leaves, oceans, sunlight, and ancient chemistry. The air feels empty, but it is really a shared inheritance shaped by countless green lives. The tallest trees on Earth rise higher than famous city towers. Coast redwoods can grow so tall that looking up from their bases feels almost unreal. The tallest known living tree, called Hyperion, reaches higher than the Statue of Liberty. These giants thrive in a narrow strip of misty coastal forest where fog helps them survive dry months. Their height is not only a marvel of growth, but a feat of physics. Water must be pulled from roots to leaves through long columns inside the trunk, working against gravity with delicate tension. At extreme heights, that task becomes harder and harder. This may place a natural limit on how tall any tree can grow. Redwoods also build enormous trunks that resist rot and fire, allowing them to keep adding height across many centuries. They show that a tree is not simply a plant. It can become a living skyscraper built from sunlight, water, and time. Some trees survive fire by hiding living buds beneath bark. Fire may seem like the end of a forest, but some trees have evolved to meet it with astonishing preparation. In certain species, small dormant buds lie protected under thick bark, or inside woody swellings. When flames scorch the outer surface, these hidden points of life can awaken. Fresh shoots emerge from trunks that looked ruined only weeks before. This strategy is common in fire-prone landscapes, where burning is not a rare disaster but a recurring force. Eucalyptus trees are famous for resprouting after intense fires, while other species keep their renewal underground in root crowns or lignotubers. The fire clears competing plants, releases nutrients, and opens sunlight. Then, the survivors return. It is a reminder that destruction in nature is sometimes also a reset. What looks like blackened silence can contain a waiting blueprint for green recovery. Trees can remember drought and prepare their offspring for stress. Plants do not remember as animals do, but they can carry traces of experience in their chemistry. When a tree survives drought, heat, or poor soil, its cells may adjust how certain genes are used. Some of these changes can influence seeds, helping the next generation respond more effectively to similar conditions. This field is still developing, but it suggests that inheritance is not only about DNA sequence. It can also involve chemical marks and stored signals shaped by the parent's environment. A seed may begin life with a kind of warning from the past. In dry regions, that could mean faster root growth, altered timing, or improved water control. The idea is powerful because it makes trees feel less passive. They are not only enduring the present. In subtle biological ways, they may be preparing descendants for the world ahead. Forests are not collections of trees, but living communities. A forest is built from relationships. Trees compete for light, but they also shape shade that protects seedlings. Fungi trade with roots. Birds spread seeds. Insects prune leaves, pollinate flowers, and feed other animals. Fallen wood becomes food for beetles and fungi, then becomes soil for the next generation. Streams carry nutrients through valleys. Predators influence herbivores, and herbivores influence which saplings survive. Even the gaps left by storms become opportunities, opening sunlit spaces where new growth begins. Nothing in this system exists alone for long. Each trunk is part of a wider pattern of exchange, pressure, loss, and renewal. That is why forests can feel so alive, even when they seem still. They are not scenery. They are societies of organisms, constantly responding to one another. To walk into one is to enter a living process that has been unfolding for millions of years. The oldest known individual tree is a bristlecone pine. In the White Mountains of California, one ancient pine has lived through nearly 5,000 winters. Its exact location is kept secret, partly to protect it from harm, but its story has already changed how people think about age. This tree grows in a place that seems almost too harsh for life, with thin soil, cold winds, and little water. Yet those difficult conditions help it survive. In richer forests, faster growth can invite rot, insects, and competition. Here, growth is slow, wood becomes dense, and damage spreads only with difficulty. The tree does not look like a giant. It looks weathered, twisted, almost half gone. But that is part of its genius. It can let dead wood remain as armor while narrow living strips keep carrying water and sugar. Its survival is not about abundance. It is about endurance refined into an art. Tree rings can preserve records of volcanoes and droughts. Each year, many trees add a new layer of wood beneath their bark. In good seasons, that layer may be wide. In hard seasons, it may be narrow or chemically unusual. By reading these patterns, scientists can reconstruct pieces of the past with astonishing detail. A severe drought can leave a thin ring across trees in a whole region. A volcanic eruption can cool the climate and create a growth signal that appears far from the volcano itself. Some rings also capture traces of unusual solar activity. Because living trees can overlap with older beams from buildings or preserved wood from ancient forests, researchers can build timelines that stretch back thousands of years. This field is like listening to history through wood. Long before thermometers, satellites, or written weather reports, trees were already recording the world, one growing season at a time. The Amazon forest recycles rain through billions of leaves. Rain does not simply fall on the Amazon and disappear into rivers. A huge portion returns to the air through the trees themselves. Roots draw water from the ground, and leaves release vapor through tiny pores. Across the scale of a rainforest, this becomes a vast upward flow, helping create clouds and feed more rainfall. Moisture can move across the basin in great atmospheric streams, passing from tree to sky to cloud to rain again. This recycling helps maintain the humid conditions that the forest needs. It also means that losing trees can affect rainfall patterns far beyond the place where cutting happens. The Amazon is not only a home for extraordinary life, it is part of a continental water engine. Every leaf is small, but together they help move water through the atmosphere with a force that can influence rivers, farms, and distant skies. Pando is a forest that may be one ancient organism. In Utah, there is a stand of quaking aspen that looks like thousands of separate trees. Beneath the ground, however, they are connected by one vast root system. This living colony is called Pando, which means I spread, and the name fits beautifully. Each trunk rises like an individual, but genetically they are copies of the same plant. When one stem dies, another can grow from the shared roots. That means the visible forest may be only the temporary surface of something much older beneath. Pando has been called one of the heaviest living organisms on Earth, and some estimates suggest its root system may have persisted for many thousands of years. It invites a strange question. Where does one tree end and another begin? In this place, the answer is not simple. The forest is both many and one, a crowd with a single hidden body. Redwood bark can grow thicker than a human arm. A coast redwood's outer covering is not just a thin skin. It can become a massive protective wall, sometimes more than a foot thick. This bark is fibrous, soft to the touch, and unusually resistant to flames. It contains very little resin, so it does not ignite as easily as many other trees. That protection matters because redwoods can live for more than 2,000 years, and across that span, fire, insects, and storms are almost certain to arrive. The bark acts like a buffer between danger and the living tissue beneath. Even when flames scar the trunk, the tree can survive if enough inner layers remain intact. This is one reason old redwoods often carry burn marks without being defeated by them. Their greatness is not only height. It is the quiet engineering of survival wrapped around them in layer after layer of reddish armor. Mangrove trees breathe through strange roots above the mud. Along tropical coasts, mangroves live where many trees would drown. Their roots stand in salty, waterlogged mud, where oxygen is scarce and the tide keeps returning. To survive there, some mangroves send special roots upward into the air. These structures can look like spikes, knees, or looping arches rising from the ground. They help the tree take in oxygen, while the lower roots remain buried in mud. Other adaptations manage salt, either by filtering it at the roots or pushing it out through leaves. This allows mangroves to grow in the uneasy border between land and sea. Their forests slow waves, shelter young fish, trap sediment, and build coastlines over time. They are not just trees at the edge of the ocean. They are living machines for survival in a place that changes twice a day with the tide. Baobab trees store water inside their swollen trunks. Across parts of Africa, Madagascar, and Australia, baobabs can look like trees from a dream, with enormous trunks and branches that seem almost root-like against the sky. Their strange shape is practical. The trunk is built to hold water during wet seasons, helping the tree endure long, dry months. Its wood is fibrous and soft, compared with many hardwoods, which allows it to swell and shrink as water stores change. Some baobabs become so wide that people have used hollow trunks as shelters, storerooms, or meeting places. They also provide fruit, leaves, bark fiber, and shade in landscapes where shade can be precious. Yet their most remarkable quality is their relationship with scarcity. Where rainfall comes unpredictably, the baobab turns its own body into a reservoir. It stands as proof that survival can be sculptural, generous, and astonishingly well adapted to thirst. Some acacia trees summon ants to fight hungry animals. In African savannas and tropical regions of the Americas, certain acacias have formed remarkable partnerships with ants. The tree offers food and shelter. It may grow swollen thorns where ants can live and produce sugary nectar that feeds them. In return, the ants patrol the branches with fierce dedication. When a browsing animal or hungry insect disturbs the tree, they rush out and bite, sting, or swarm the intruder. Some ants even clear away competing plants around the base, protecting their host's access to sunlight and nutrients. This relationship can look almost like a tiny security force hired by a tree, but it is built by evolution, not intention. Each partner gains something valuable. The ants receive a home and steady food. The tree receives protection in a landscape full of mouths. It is one of nature's most vivid examples of defense through alliance. Aspen leaves tremble because their stems are unusually flattened. A quaking aspen gets its famous shimmer from the shape of its leaf stalks. Instead of being round and stiff, they are flattened from side to side. This allows even a slight breeze to twist the leaves back and forth, making the whole tree flicker with movement. The effect is beautiful, but it may also be useful. Moving leaves can reduce overheating, change how light reaches the surface, and perhaps make it harder for some insects to settle. The trembling also gives aspen groves their distinctive sound, a soft flutter that can fill a mountainside. Because aspens often grow in connected colonies, a breeze can pass across many trunks at once, setting thousands of leaves into motion. What looks like nervousness is really anatomy meeting air. The tree has not learned to shiver. It was built so the wind can play through it. A single tree can host thousands of other living species. An old oak is more than one organism standing in a field. It can be an entire neighborhood. Birds nest in its branches. Beetles tunnel through deadwood. Lichens and mosses cling to the bark. Fungi work inside fallen limbs. Caterpillars feed on leaves, and those caterpillars feed young birds. Tiny wasps, spiders, mites, and microbes occupy spaces so small we barely notice them. Cavities can shelter bats, owls, squirrels, or bees. Even the roots shape a world below ground, where worms, fungi, and bacteria process fallen leaves into soil. The older and more complex the tree becomes, the more lives it can support. Dead parts are not useless. They often become the richest habitats of all. To cut down one mature tree can mean removing a vertical ecosystem, a layered world that took decades or centuries to assemble. Eucalyptus trees can help spread fire with flammable oils. In Australia, many eucalyptus forests are shaped by fire, and the trees themselves contain oils that burn readily. On hot days, these vapors can add to the sharp scent of the bush. During extreme conditions, fallen leaves, peeling bark, and oil-rich material can help flames move quickly through the landscape. Some species shed long ribbons of bark that may carry fire upward into the canopy. Yet the story is not simply one of danger. Many eucalyptus trees are also built to recover after burning. They can resprout from protected buds or underground structures, returning green growth to blackened trunks and soil. Fire has been part of many Australian ecosystems for a very long time, and eucalyptus trees show both sides of that relationship. They can intensify the flames and then emerge again from the aftermath with astonishing speed. Some trees drop branches when they need to save water. In hot and dry conditions, a tree may sacrifice part of itself to protect the whole. Certain species can shed leaves, twigs, or even larger branches during severe stress. This reduces the amount of living tissue that needs water, and it lowers the surface area where moisture can escape. To us, a fallen limb may look like injury or failure. For the tree, it may be a controlled retreat. Eucalypts are sometimes associated with sudden branch fall, especially during heat or drought, although the reasons can be complex. Other trees reduce their crowns more gradually. The principle is powerful either way. A tree is not fixed in the shape it happens to have. It can reorganize its body around survival. In a dry year, losing a branch may be less like defeat and more like dropping cargo from a ship in a storm. The dragon blood tree bleeds a deep red resin. On the island of Socotra, the dragon blood tree grows with a crown shaped like an umbrella turned toward the sky. When its bark is cut, it can release a dark red resin that once inspired legends of dragons, wounds, and magic. People have used this resin for dyes, varnishes, medicines, and rituals across centuries. Its unusual color made it valuable in trade, while the tree itself became one of the most striking symbols of Socotra's rare biodiversity. The umbrella shape is not only beautiful, it helps shade the roots and capture moisture in a dry, rocky landscape. Like many island species, it belongs to a world shaped by isolation. Its form, resin, and survival strategy feel almost ancient because they are so unlike familiar trees. It shows how evolution can turn hardship into something unforgettable. The sandbox tree fire seeds with explosive force. In tropical America, the sandbox tree carries seed capsules that can burst apart with a sharp crack. When they dry and split, the sections fling seeds away from the parent tree at remarkable speed. This violent launch helps spread the next generation beyond the shadow of the crown, where competition would be strongest. The tree has other dramatic features too. Its trunk is covered with pointed spines, and its sap can irritate skin and eyes. Historically, parts of the dried fruit were used as small containers for fine sand, which helped give the tree its common name. But the seed explosion is what captures the imagination. Plants are often described as passive, yet this tree turns tension, drying, and structure into motion. It does not chase the future. It fires it into the forest. Bristlecone pines survive by letting parts of themselves die. In the harsh high country where bristlecones grow, survival often means becoming less rather than more. A tree may keep only a narrow strip of living tissue active, while much of the trunk stands dead, silvered by wind and sun. This might sound like decay, but it can be a strategy. If one section is damaged by cold, drought, or lightning, the remaining living strip can continue carrying water to a small crown of needles. The dead wood does not vanish quickly because it is dense, resinous, and exposed to dry mountain air. It becomes a sculpted shield around the life that remains. This creates the haunting forms bristlecones are famous for, half alive and half monument. They reveal a different kind of success. Not lushness, not speed, but the ability to shrink the living self down to what can endure. Fig trees can begin life high in another tree. Some figs start as seeds dropped by birds or bats in the branches of a host tree. There, high above the ground, a tiny seedling germinates in a pocket of debris. Instead of beginning in soil, it begins in the sky. Its roots grow downward, seeking the forest floor, while its leaves reach for light in the canopy. Over time, some species wrap around the host with a lattice of roots and stems. The original tree may eventually be shaded, squeezed, or outcompeted. What began as a passenger can become a towering structure in its own right. This life strategy is dramatic, but it makes sense in dense tropical forests where sunlight at ground level is scarce. By starting above the shadows, the young fig skips part of the struggle. It turns another tree into a ladder, then builds its own future around it. Some trees flower only after decades of quiet growth. For many trees, flowering is not a yearly performance. It can be a long-delayed event, reached only after enough stored energy, size, and environmental timing come together. Some tropical trees may wait many years before their first bloom. Others flower heavily only in certain seasons, sometimes with many individuals blooming at once across a whole forest. This mass flowering can overwhelm seed predators and attract pollinators in great numbers. In orchards, a fruit tree's first blossoms can mark the end of a patient juvenile phase. In wild forests, flowering may be tied to rainfall, temperature, day length, or internal rhythms scientists are still studying. The result is a hidden suspense written into wood. For years, a tree may appear simply to be growing. Then one season, almost suddenly, it enters a new life stage and opens itself to the future through flowers. The ginkgo tree has survived since the age of dinosaurs. The ginkgo is often called a living fossil, and for good reason. Its fan-shaped leaves appear in fossils from deep prehistoric time, when dinosaurs still walked beneath ancient skies. Today, only one living species remains, but its lineage once included many relatives spread across the world. The modern tree survived in part because people cultivated it near temples, gardens, and streets, especially in East Asia. It is tough, long-lived, and surprisingly tolerant of pollution, which is why ginkgos now grow in cities far from their original refuge. In autumn, their leaves turn a clear golden yellow, falling in bright carpets that feel almost ceremonial. To look at a ginkgo is to see a survivor from a vanished botanical world. It is not unchanged in every detail, but it carries an ancient design into the present, quietly bridging modern streets and Mesozoic forests. Willow bark helped inspire one of the world's common medicines. Long before modern pharmacies, people noticed that willow bark could ease pain and fever. The bark contains compounds related to salicylic acid, a substance that helped inspire the development of aspirin. Ancient cultures used willow preparations in different ways, and later, chemists learned how to refine and modify the active chemistry into a more reliable medicine. The story is a beautiful example of how close observation of plants can shape human knowledge. A tree growing beside rivers and streams became part of medical history because people paid attention to what it could do. That does not mean chewing bark is the same as taking a carefully made tablet, and dosage matters greatly. But the connection remains fascinating. Hidden within a tree's defenses was a molecule that humans turned into one of the most widely used medicines in the world. Oak trees support more wildlife than many other native trees. In many temperate landscapes, an oak is a powerhouse of biodiversity. Its leaves feed hundreds of kinds of caterpillars, which in turn become essential food for nesting birds. Its acorns nourish jays, squirrels, deer, mice, and many other animals. Its bark, cracks, dead limbs, and hollows create homes for insects, fungi, bats, and birds. A mature oak can become a seasonal banquet, a shelter, and a breeding ground all at once. Part of its value comes from long relationships with local wildlife. Many species have evolved alongside oaks for thousands of years, learning to use their leaves, wood, fruit, and shade. Even after death, an oak continues to support life as its timber slowly breaks down. This makes it more than a tree in an ecological sense. It is a foundation species, holding up a crowded world of lives. Cedar wood can resist decay for astonishingly long periods. Cedar has been prized for centuries because its wood can last in conditions that would quickly ruin many others. Natural oils and chemical compounds help resist fungi and insects, giving it a durability that made it useful for buildings, boats, chests, shingles, and ceremonial objects. Different trees share the cedar name, and their properties vary, but many have a reputation for fragrance and longevity. The scent that people enjoy in cedar closets is part of the same chemistry that helps protect the wood. In some cultures, cedar became more than a material. It became a tree of shelter, craft, and meaning. Its trunks could become homes, canoes, masks, or sacred spaces. What makes it fascinating is that its strength is not brute hardness alone. It is chemistry woven into grain, allowing the tree's body to keep serving long after it falls. Tree roots can recognize close relatives in the soil. A forest floor may seem like a tangle of roots all searching for the same water and minerals, but experiments suggest some plants can behave differently around kin. When seedlings grow beside close relatives, their root growth may be less aggressive than when they grow beside strangers. This does not mean a tree has family feelings, but it does show that roots can detect chemical differences in their surroundings. The soil is full of signals from neighboring plants, microbes, and fungi. Roots read that world through touch, moisture, nutrients, and molecular traces. In crowded places, this recognition could help related plants avoid wasting energy on direct competition. It may also shape how young trees share space beneath the surface. What looks like blind growth is far more responsive than it appears. Roots are not simply anchors. They are sensing organs exploring a dark and crowded world. Leaves can turn sunlight into sugar with elegant precision. Inside every leaf, sunlight enters a living factory so small that it takes a microscope to see its machinery. Chloroplasts capture light and use its energy to rearrange simple ingredients from air and water. Carbon dioxide becomes the backbone of sugar, and that sugar becomes the fuel for wood, roots, flowers, fruit, and repair. The process is astonishing because it turns something weightless, light falling from the sky, into the body of a tree. A trunk is not built mainly from soil. Much of its substance comes from carbon gathered from the air. This means that when you touch wood, you are touching atmosphere transformed by sunlight. Leaves do this work while also managing heat, water loss, and damage from too much brightness. They are delicate surfaces, but they run one of the most important chemical processes on Earth. Trees move water upward without a beating heart. A tall tree has no pump like an animal heart, yet it can lift water from underground roots to leaves far above the ground. The secret lies in narrow tubes inside the wood and the pulling force created when water evaporates from leaves. As moisture leaves through tiny pores, it draws more water upward behind it, like a continuous thread under tension. Water molecules cling to each other, and they also cling to the walls of the tree's internal vessels. Together, these forces allow a silent climb against gravity. The system is powerful, but fragile. If air bubbles break the chain, water transport can fail in that part of the wood. Still, trees perform this feat every day, moving vast amounts of water without muscles, valves, or a pulse. Their stillness hides a remarkable act of physics. A redwood can drink fog through its leaves. Along the misty coast of California, summer fog is more than atmosphere. It can be a lifeline. Coast redwoods live in a region where dry months arrive just when the trees are still towering into warm light. Fog helps solve that problem. Moisture collects on needles and branches, then drips down to the soil below. Even more astonishing, redwood leaves can absorb some water directly from fog. This helps reduce drought stress in trees that may stand taller than a cathedral spire. The forest itself becomes a fog catcher, turning drifting cloud into usable water. Smaller plants, mosses, and animals benefit from the same hidden gift. In this way, a redwood is connected not only to soil and rain, but to the marine layer rolling in from the Pacific. Its survival is written partly in mist. Some desert trees grow roots deeper than buildings are tall. In arid landscapes, water may hide far below the surface, beyond the reach of ordinary plants. Certain desert trees answer with roots that descend astonishing distances. Mesquite, for example, can send roots deep enough to tap groundwater, where shallow-rooted plants would fail. Above ground, the tree may look modest, with small leaves and thorny branches. Below ground, it can be an explorer, following moisture through layers of dry earth. This deep access allows it to remain green when the surrounding land appears exhausted. The strategy also stabilizes soil and provides food or shelter for insects, birds, and mammals. Desert survival is often imagined as toughness alone, but here it is also architecture. The tree builds downward into darkness. Its hidden life may be larger and more daring than the shape we see above the sand. Tree bark is a living shield against heat and insects. Bark is often mistaken for dead covering, but it is a complex boundary between a tree and the outside world. The outer layers can block heat, slow water loss, and make it difficult for insects to enter. Beneath them, living tissues move sugars from leaves to roots and help maintain the tree's growth. Different species build bark for different dangers. Some make it thick against fire. Some make it flaky to shed pests. Some fill it with bitter or aromatic compounds that discourage hungry mouths. Bark also records age and weather in ridges, cracks, scales, and plates. It is the tree's armor, clumping protection, and weatherproofing all at once. When you look closely at bark, you are seeing a survival strategy written in texture. Every groove and layer has been shaped by attack, climate, and time. The smell of pine forests comes from protective tree chemicals. That clean, resinous scent in a pine woodland is not made for human enjoyment. It comes from volatile compounds produced by the trees, many of which help defend needles, bark, and wood. These chemicals can discourage insects, slow fungal attack, and seal wounds as sticky resin. When warm air rises through a forest, the compounds evaporate and drift around us as fragrance. They also take part in atmospheric chemistry, where they can help form tiny particles that influence haze and cloud processes. What we experience as a pleasant forest smell is actually a hint of an invisible chemical life. The trees are not perfuming the air for beauty. They are protecting themselves, communicating stress and interacting with the atmosphere. A pine scent can feel calming, but it is also evidence that the forest is active, guarded, and chemically awake. Some trees release scents that warn their neighbors about insects. When caterpillars or beetles begin feeding, damaged leaves can emit specific airborne chemicals. Nearby trees may detect those cues and alter their own defenses before the attackers arrive. They might thicken tissues, produce bitter compounds, or change the chemistry of leaves in ways that make feeding less rewarding. This response has been studied in several plant groups, and it reveals a world of warning carried by scent. The message is not intentional in the way a human warning is intentional, but it still affects behavior. One plant's injury becomes another plant's preparation. Air becomes a channel for survival. To a person, a breeze through leaves may seem empty. To plants, it may carry information about danger, opportunity, and change. Forests are not silent green backdrops. They are filled with chemical signals moving through the air above our heads. Roots can change direction when they sense gravity and moisture. A root tip is tiny, but it is an impressive navigator. As it grows, it senses gravity so it can move downward, and it detects moisture so it can turn toward better water. Specialized cells near the tip help guide this movement, while the growing region bends in response. The process is slow enough to escape our notice, yet constant enough to shape the entire life of the tree. Roots can also avoid obstacles, branch in nutrient-rich patches, and respond to signals from microbes. This means the underground part of the tree is not a passive mass spreading at random. It is a searching system. Every millimeter of growth is a decision shaped by the environment. In darkness, without eyes, roots map the world through pressure, chemistry, water, and gravity. They find paths the tree will depend on for decades. A tree's crown can avoid touching neighboring crowns. In some forests, the upper branches of neighboring trees leave narrow gaps between one another. From below, the canopy can look as though it has been cracked into pieces, with winding channels of sky separating each crown. Scientists have several ideas about why this happens. Branches may avoid damage from rubbing during wind. Leaves may respond to shade or changes in light quality near a neighbor. Insects and disease might spread less easily when crowns do not touch. Different species may produce the pattern for different reasons. Whatever the cause, the effect is striking. Trees that seem to be reaching in every direction still leave space at their edges. The canopy becomes a living mosaic, shaped by motion, light, and competition. It reminds us that trees have boundaries, even when those boundaries are drawn not by walls, but by air. The crown shyness phenomenon leaves rivers of sky between trees. Look upward in certain forests, and you may see a pattern that feels almost designed. The crowns fit near one another without fully closing, leaving bright branching paths overhead. This is called crown shyness, and it is one of the most beautiful examples of forest structure. It has been observed in mangroves, eucalyptus, camphor trees, and other species. The gaps can form between individuals of the same species, and sometimes between different species as well. Wind may cause outer twigs to collide and break, trimming the edges like natural pruning. Light sensitivity may also guide growth away from neighboring leaves. The result is a canopy that seems to respect invisible borders. It is not politeness, but biology and physics working together. Those lines of sky reveal that even high above the ground, a forest is negotiating space. Strangler figs can slowly replace the tree that raised them. A young strangler fig often begins high in the canopy, where an animal has dropped its seed in a branch fork. At first, it is only a small plant using another tree for support. Then its roots descend toward the ground, growing longer and stronger with each season. Once they reach soil, the fig gains access to water and minerals. Its stems thicken around the host, and its leafy crown expands into the sunlight. Over many years, the original tree may lose light, space, and strength. Sometimes it dies and decays away, leaving the fig standing as a hollow lattice. This strategy sounds ruthless, but it is also a brilliant solution to life in a shaded rainforest. Instead of struggling upward from the dark forest floor, the fig begins closer to the light. It turns another tree's height into its own beginning. Some trees seal wounds rather than truly healing them. When an animal is cut, new tissue can close the injury and restore the surface. Trees work differently. If bark is broken or a branch is torn away, the damaged wood does not become healthy again. Instead, the tree builds barriers around the injury. It walls off the affected area with chemical and structural changes, then grows new tissue around the edges. Over time, the wound may be covered, but the old damage remains sealed inside. This process helps stop decay from spreading through the trunk. A knot in a board can be the old base of a branch that the tree grew around. A hollow trunk may still stand because the living outer layers continue working while the center has been isolated. Tree repair is therefore not erasure. It is containment, adaptation, and growth around loss. Trees can count cold days before opening spring buds. Many temperate trees do not open their buds simply because one warm afternoon arrives. That would be dangerous, since a late frost could destroy tender leaves and flowers. Instead, they use seasonal cues. Some need a certain amount of winter chilling before they become ready to respond to warmth. After that, they track rising temperatures and lengthening days. Only when the signals fit does the bud begin to open. This timing can be astonishingly precise, and it has evolved to match local climates. A tree is rooted in place, so getting spring wrong can be costly. Climate change is now complicating these old rhythms in some regions because warmth and frost patterns may shift unevenly. Bud break may look like a simple green arrival, but it is the result of careful biological timing. Each spring leaf is a decision made from winter's memory. Birch bark can burn, even when it is damp. Birch bark has helped people start fires in cold northern landscapes for generations. Its papery outer layers contain oils and resins that can catch flame more easily than many damp materials. Even after rain, the outer bark may peel away in thin sheets that burn well enough to light kindling. This property made birch valuable to travelers, hunters, and communities living in boreal regions. The bark also has other remarkable qualities. It is water-resistant, flexible, and was used historically for containers, coverings, writing surfaces, and canoes. On the living tree, those same layers help protect against cold, pests, and moisture. The pale surface reflects light, while darker marks reveal breathing pores and scars. Birch bark shows how a protective skin can become a human tool. Something evolved, for the tree's survival became part of our own ingenuity. The quaking aspen can clone itself across entire landscapes. A single aspen tree may be only the visible stem of a much larger underground life. Aspens often reproduce by sending up new shoots from spreading roots. Over time, this can create groves of genetically identical trunks, each one rising separately but connected below. In autumn, these clonal patches may reveal themselves when all their leaves turn color at the same time. One group glows gold, while another nearby remains green, because each clone follows its own internal timing. This way of growing helps aspens recover after fire, grazing, or storms. If trunks are destroyed, the root system can send up a new generation. The landscape may look like a forest of individuals, but some parts are really repeated expressions of the same plant. Aspens remind us that a tree can be both a momentary stem and a long-lived hidden presence beneath the soil. Some trees survive lightning strikes and keep growing afterward. Lightning can blast bark from a trunk, split wood, boil sap, and leave a scar running from crown to ground. For many trees, the damage is fatal. Others survive if the strike travels through part of the outer trunk and leaves enough living tissue intact. A scar may remain for the rest of the tree's life, gradually widening as new growth forms around it. Sometimes the wound becomes an entry point for fungi or insects. Sometimes the tree walls off the damage and continues for decades. In forests, lightning can also shape the wider community by killing one tall tree and opening a patch of light below. That sudden gap may allow seedlings to surge upward, so a single flash can injure, kill, or transform. A surviving tree carries the mark like a vertical memory of the sky touching earth. The tree line marks where cold defeats upright forests. Climb high enough on a mountain, or travel far enough toward the poles, and forests begin to thin. Eventually, upright trees give way to shrubs, grasses, mosses, and open ground. This boundary is called the tree line. It is not drawn by one factor alone. Low temperatures, short growing seasons, wind, snow, ice, and poor soil all play a role. Above the limit, seedlings may germinate but fail to grow tall before winter returns. Some trees survive there only as twisted, low forms pressed close to the ground. The boundary can move over time as climate shifts, which makes it an important signal for scientists studying environmental change. To stand at a tree line is to stand at the edge of what a tree body can manage. Beyond it, the shape of life must change. Cloud forests catch drinking water straight from passing mist. High on tropical mountains, clouds can drift through the trees instead of above them. Leaves, mosses, branches, and epiphytes collect tiny droplets from the mist. The water gathers, drips, and runs down into soils, streams, and springs. In some places, this cloud capture is a major part of the local water supply, especially during seasons when rainfall is lower. The forest acts like a living net stretched across the mountain air. Its surfaces slow the wind and comb moisture from passing cloud. Remove the trees, and that hidden source of water can weaken. Cloud forests also shelter rare species found nowhere else, partly because their cool, wet conditions are so specific. They are among the most magical ecosystems on Earth, not because they are imaginary, but because their biology literally draws water from the sky. Tropical trees can grow colorful buttress roots for support. In rainforests, many large trees have wide, flaring roots that rise above the ground like wooden fins. These buttress roots help support tall trunks in shallow tropical soils, where nutrients are often concentrated near the surface rather than deep below. Instead of sending one great taproot far downward, the tree spreads stability outward. Some buttresses are taller than a person, forming walls, alcoves, and twisting corridors around the base. They can be smooth, ridged, pale, dark, or stained with moss and minerals. Animals use them as pathways and shelters. People have used them as landmarks, drum surfaces, and hiding places. Their shape turns engineering into sculpture. A rainforest giant must hold itself upright through storms, weight, and competition for light. Buttress roots are the visible solution, a foundation lifted into view, showing the architecture that keeps the canopy standing. The kapok tree can tower above the rainforest canopy. In tropical forests of Central and South America, the kapok can rise like a living mast above the surrounding green. Its trunk may be wide, pale, and supported by great buttress roots, while its crown opens high in the sunlight, where many other trees never reach. This height gives it access to bright air above the shaded understory, but it also makes the tree an entire vertical world. Birds perch in its branches. Insects visit its flowers. Animals may travel through its crown without touching the ground. Its seed pods contain silky fibers that help the seeds drift and have also been used by humans for stuffing and insulation. In many cultures, the kapok became a symbol of connection between earth and sky. It is not only tall, it is a landmark, a habitat, and a reminder that forests have architecture. Some trees rely on bats to pollinate their flowers. After sunset, when bees and butterflies are gone, another kind of pollinator begins its work. Many tropical trees open large, pale, strongly scented flowers at night, perfectly suited to bats. These flowers often hang away from dense foliage, making them easier to reach in flight. A bat pushes its face into the bloom to drink nectar, and pollen dusts its fur. When it visits another flower, that pollen travels with it. This partnership helps produce fruit for animals and seeds for future forests. Durian, baobab, and several other trees depend partly or heavily on nocturnal visitors. It is a beautiful exchange, but also a fragile one. Remove the bats, and some trees may lose one of their most important links in reproduction. The night forest is not empty. It is busy with wings, scent, hunger, and renewal. Brazil nut trees depend on wild bees and forest rodents. A Brazil nut may seem like a simple snack, but its life story is tangled with the rainforest. The tree's flowers have a special structure that can only be pollinated by strong-bodied wild bees capable of lifting part of the bloom. Without those bees, the tree produces few nuts. Then comes the fruit itself, a heavy wooden capsule that falls to the forest floor. It is so tough that most animals cannot open it. Agoutis, small, sharp-toothed rodents, can gnaw through the shell and carry away the seeds. Some are eaten, but others are buried and forgotten, giving new trees a chance to grow. This means a Brazil nut tree relies on both tiny pollinators and hungry mammals. Its survival is not an isolated achievement. It is a chain of relationships, hidden inside one hard, round fruit. The manchineel tree produces fruit that looks dangerously inviting. On some Caribbean and Central American shores grows a tree with glossy leaves and small green fruits that can resemble apples. Yet it is one of the most hazardous trees in the world. Its sap contains irritating compounds that can blister skin, and rain dripping from its leaves can carry enough sap to cause pain. The fruit is especially dangerous because its pleasant appearance gives no obvious warning. Stories of the manchineel often sound exaggerated, but the tree's defenses are real and powerful. They discourage animals from eating or damaging it, and they have earned the tree warning signs in places where people might approach. Even so, it plays a role in coastal ecosystems by stabilizing sandy soils and providing shelter. The lesson is unforgettable. In nature, beauty and danger can share the same branch, and not every fruit is an invitation. Some trees make natural latex as a defense against damage. When the bark or leaves of certain trees are cut, a milky fluid seeps out. This latex is not simply tree blood, although it can look strangely alive as it flows. It is a defensive mixture that may contain sticky, bitter, or toxic compounds. For insects, it can gum up mouthparts or make feeding unpleasant. For the tree, it helps seal small wounds and protect exposed tissue. Different plant families have evolved latex independently, which shows how useful this strategy can be. In some species, the fluid hardens when exposed to air, forming a protective barrier. Humans later learned to use latex in extraordinary ways, but its original purpose was survival. Every white drop is part of a chemical defense system. The tree cannot run from damage, so it responds by releasing a liquid shield. Rubber trees changed transport, industry, and global history. The rubber tree of the Amazon produces latex that humans transformed into one of the most important materials of modern life. Once people learned how to stabilize rubber, it became essential for tires, seals, belts, gloves, hoses, and countless machines. Bicycles, cars, aircraft, and factories all depended on its flexible strength. The demand reshaped economies, forests, and colonial histories, often with great human cost. Seeds were eventually taken from South America to plantations in Asia, shifting the center of production across the world. It is astonishing to think that the bounce of a tire, the grip of a wheel, and the seal inside a machine can trace back to a tree's wound response. A forest defense became an industrial foundation. The story is both brilliant and troubling, because it shows how a botanical discovery can move through technology, trade, power, and everyday life. Olive trees can live for thousands of fruitful years. Around the Mediterranean, old olive trees can look more like weathered sculptures than ordinary plants. Their trunks twist, split, hollow, and thicken into shapes made by centuries of drought, pruning, wind, and harvest. Yet even very old trees can still produce olives when cared for. This longevity made them symbols of peace, endurance, food, and continuity. Their fruit gave oil for cooking, lamps, medicine, trade, and ritual. An olive grove could connect generations, with one family tending trees planted by ancestors they never met. Part of the tree's strength lies in its ability to resprout from old wood and survive poor, rocky soils. It does not need lush abundance to keep giving. The olive teaches a different kind of richness. It grows slowly, lives long, and turns harsh sun and thin earth into nourishment that helped shape civilizations. Apple trees traveled the world with humans and animals. The apple's journey began in the mountains of Central Asia, where wild trees produced fruits of many sizes, colors, and flavors. Bears, horses, and other animals helped spread the seeds, while people later carried apple varieties along trade routes and migration paths. Because apples grown from seed do not usually match their parents, humans learned to preserve favorite kinds through grafting. A branch from one excellent tree could be joined to another rootstock, allowing the same flavor to travel across centuries. This is why named varieties can have histories of their own. Apples became food, drink, medicine, myth, and symbol. They crossed oceans in ships and took root in orchards around the world. Every crisp bite carries a story of wild forests, animal appetites, human selection, and patient cultivation. Few fruits are so familiar, yet so historically restless. The Bodhi tree became a sacred symbol of awakening. In the Buddhist tradition, Siddhartha Gautama attained enlightenment while seated beneath a fig tree in Bodh Gaya. That tree, known as the Bodhi tree, became one of the most meaningful trees in human history. Its heart-shaped leaves and spreading shade came to represent wisdom, meditation, and liberation from suffering. Descendants and symbolic plantings have been cared for across Asia for centuries, turning living trees into links between memory and devotion. Scientifically, the Bodhi tree is a kind of sacred fig, a species that can support wildlife through its fruit and provide shade in warm climates. Culturally, it shows how deeply trees enter human imagination. A tree can be more than wood, leaves, and roots. It can become a place where a story gathers, where people return to reflect, and where the natural world becomes part of spiritual history. Ancient yews can outlive churches built beside them. In parts of Britain and Europe, old yew trees stand in churchyards with trunks that look carved by age itself. Some may be older than the buildings beside them, and possibly older than the Christian sites that later formed around them. Yews can live for extraordinary spans because they grow slowly, tolerate heavy pruning, and sometimes renew themselves from within. Their trunks may hollow while living tissue continues around the outside. Branches can root where they touch the ground, creating new growth from the old tree's own body. Their dark needles and red arrows made them powerful symbols of death, endurance, and rebirth. They also provided wood for longbows, linking them to warfare and craft. An ancient yew is not only a botanical survivor, it is a witness to changing belief, language, landscape, and generations of human footsteps. Some hollow trees remain alive for centuries after losing heartwood. A tree does not need its center to keep living. The most active tissues are closer to the outside, where water moves upward and sugars move down from leaves. The inner heartwood can decay or disappear, leaving a hollow trunk, while the living outer ring continues to function. This is why some ancient trees stand with openings large enough for animals or even people to enter. The hollow may look like weakness, but it can also reduce weight and help the tree flex in wind. At the same time, the cavity becomes habitat for many species. Fungi, insects, birds, bats, and small mammals all use these spaces. A hollow tree is therefore not simply damaged, it is transformed. Its missing center becomes part of the forest's living richness, while the tree itself may keep growing year after year. Tree hollows become nurseries for owls, bats, and insects. A cavity in an old trunk can be one of the most valuable homes in a forest. Many animals cannot create hollows themselves, so they depend on age, decay, broken branches, and woodpecker work to make shelter. Owls may nest inside them. Bats may roost there by day. Bees can build colonies in protected spaces. Beetles, moths, spiders, and many other creatures use the damp wood and sheltered cracks. These hollows often form slowly, sometimes over decades, which makes old trees especially important. A young plantation may have trunks, leaves, and shade, but it often lacks these hidden rooms. When ancient trees are removed, entire communities can lose breeding sites. The value of a hollow is easy to miss from the outside. Inside, it may hold eggs, wings, larvae, warmth, and the next generation of forest life. Fallen logs can feed forests for hundreds of years. When a large tree falls, its work is not finished. The trunk becomes a long feast for fungi, beetles, bacteria, and countless small animals. As the wood softens, it stores moisture like a sponge, shelters seedlings, and releases nutrients back into the soil. Mosses and lichens spread across its surface. Salamanders may hide beneath it. Insects tunnel through it, and birds arrive to feed on them. In cool or wet forests, this slow breakdown can take generations. The log changes from solid timber to crumbly wood, then to dark soil that nourishes new growth. To remove every fallen trunk from a woodland is to remove part of its future. Dead wood is not waste. It is a bank of energy and minerals, paying itself back to the forest slowly, quietly, and with astonishing generosity. Nurse logs help young trees grow from dead wood. In damp forests, seedlings often sprout on fallen trunks instead of directly on the ground. These nurse logs lift young plants above heavy leaf litter and give them access to moisture stored in decaying wood. As the old trunk breaks down, it releases nutrients that feed the new roots. The seedling may eventually send roots down around the log into the soil below. Many years later, after the nurse log has rotted away, the grown tree can stand on raised roots like stilts, preserving the ghost shape of the wood that helped it begin. This is one of the forest's most beautiful cycles. A dead tree becomes a cradle. Its body, softened by fungi and rain, gives structure and food to the next generation. In such places, death is not an ending. It is a platform. Forest soil holds more life than most people imagine. Beneath a single footstep, the ground may contain a universe of organisms. Bacteria process chemicals too small for us to see. Fungi spread fine threads through leaf litter. Nematodes, mites, springtails, worms, beetle larvae, and countless other creatures break down organic matter and move nutrients through the soil. This hidden community helps decide how forests grow. It recycles fallen leaves, builds soil structure, stores carbon, and supports roots. A handful of healthy forest soil can contain more living individuals than there are people in a city. The drama is mostly microscopic, but its effects are enormous. Without this underground life, fallen material would pile up, and nutrients would remain locked away. Trees may dominate the view above ground, but below them is a crowded living engine. The forest does not stand on dirt. It stands on a breathing, feeding world. Mycorrhizal fungi can trade minerals for sugars from tree roots. Many tree roots are wrapped or entered by mycorrhizal fungi. This partnership is one of the great alliances in land-plant evolution. The fungi spread through soil in fine threads, reaching spaces that roots cannot easily explore. They gather phosphorus, nitrogen, and other minerals, then pass some of them to the tree. In exchange, the tree gives sugars made through photosynthesis. This trade can shape which trees thrive, how seedlings establish, and how nutrients move through forests. Some fungi specialize with particular tree groups, while others connect with many partners. The relationship is not always perfectly equal. Each side can reward, limit, or compete depending on conditions. Still, the basic bargain is extraordinary. Sunlight captured in leaves travels down to roots, then into fungi. Minerals gathered in darkness travel back upward into living wood. A forest is built on trades we rarely see. Some trees share carbon with shaded seedlings below them. In dense forests, young seedlings often live in deep shade, where making enough sugar is difficult. Studies have found that carbon can move from larger trees to smaller plants through shared underground fungal connections. This does not mean every seedling is being lovingly fed, and scientists continue to debate how common or important this transfer is in different forests. But the possibility changes the emotional shape of the woodland. A young plant hidden under a canopy may not be entirely alone. It may be connected to a wider web of exchange, receiving small amounts of support while waiting for a gap in the light. The transfer begins with sunlight high in the leaves of an adult tree. It moves into sugar, then root, then fungus, then another root. What looks like darkness below the canopy may contain a subtle flow of energy. A dying tree may pass resources to nearby relatives. As a tree declines, its remaining tissues and root connections may still move carbon and nutrients through the soil community. In some cases, related neighboring trees appear to receive resources through shared fungal networks before the dying individual is gone. The science is complex, and forests are full of competition as well as cooperation. Yet the image is powerful because it shows that death in a forest can be connected to continuation. A weakening tree may become less of a solitary body and more of a source. Its leaves fall. Its wood becomes habitat. Its roots decay into food. Some of its stored energy may even move outward while it still lives. Nothing is wasted quickly. The forest absorbs endings and turns them into beginnings. A dying tree does not simply vanish from the story. It is redistributed into the lives around it. Forests can cool cities by several degrees during heat waves. In a hot city, shade can be more than comfort. It can be protection. Trees cool urban spaces in two main ways. Their crowns block sunlight from roads, walls, and pavements that would otherwise absorb and radiate heat. Their leaves also release water vapor, which cools the surrounding air as it evaporates. Together, these effects can lower local temperatures noticeably, especially in neighborhoods with dense canopy cover. This matters during heat waves, when exposed streets can become dangerous for older people, children, outdoor workers, and anyone without reliable cooling indoors. Earthen forests also make walking more pleasant, reduce glare, and soften the hard surfaces of the built environment. A street lined with trees is not just prettier than a bare one. It can be physically safer. In a warming world, leaves are becoming part of public health. Urban trees can filter pollution from busy streets. City trees stand in some of the most stressful growing conditions imaginable, yet they still perform valuable work. Leaves and bark can capture particles from traffic, construction, and industry. Some gases enter leaves through tiny pores, where they may be absorbed or chemically changed. The effect varies with species, street layout, weather, and pollution type, but trees can help improve the air around them when planted wisely. Their role is not magic, and they cannot replace reducing emissions at the source. Still, they add a living layer of defense between people and the harsh chemistry of roads. They also slow stormwater, reduce noise, support birds and insects, and make neighborhoods feel more livable. A roadside tree is enduring heat, salt, compacted soil, and exhaust. While rooted in concrete edges, it is still quietly working for the lungs of the city. Tree roots can help hold riverbanks in place. Along rivers, tree roots do more than drink from the wet soil. They grip it. Fine roots bind loose particles together, while larger roots act like living cables through the bank. During floods, when rushing water tries to tear earth away, this hidden structure can slow erosion and help keep the river's edge intact. Overhanging roots also create shaded pockets where fish can hide from heat and predators. Fallen leaves feed aquatic insects, and those insects feed fish and birds. A riverside tree is therefore part of the river itself. It shapes the bank, cools the water, feeds the food web, and influences how the channel changes over time. Remove too many trees, and a stream can become warmer, muddier, and less stable. The roots you cannot see may be holding together an entire waterside world. Mangrove forests protect coastlines from storms and erosion. Where tropical seas meet muddy shores, mangroves stand in tangled ranks with roots that slow waves and trap sediment. During storms, this living barrier can reduce the force of water before it reaches inland communities. The roots break up currents, hold soil in place, and help build land over time by catching silt and organic matter. They also provide nurseries for fish, crabs, and shrimp, which shelter among the roots when young. Their value is not only ecological. In many coastal regions, mangroves protect homes, fisheries, and livelihoods. Cutting them away can leave shorelines more exposed to erosion and storm surge. They live in salt, heat, mud, and shifting tides, yet their presence makes the coast more stable. A mangrove forest is not just vegetation at the water's edge. It is a living seawall, nursery, and coastline builder. Trees can lock carbon away inside wood for centuries. A tree builds itself partly from carbon dioxide pulled from the air. Through photosynthesis, that carbon becomes sugars, then cellulose, lignin, bark, roots, and heartwood. As long as the tree lives, much of that carbon remains stored in its body. If the wood becomes part of a long-lasting building or a slowly decaying forest log, some can remain out of the atmosphere for generations. This is one reason forests matter in climate systems. They are not only places of beauty and habitat, they are reservoirs of carbon held in trunks, branches, roots, and soil. The story is not simple because fire, decay, logging, and regrowth all change the balance. But the basic wonder remains. A tree can take an invisible gas and turn it into a solid pillar. Wood is, in a real sense, captured air given strength. Peat swamp forests store enormous carbon beneath waterlogged ground. In peat swamp forests, the greatest treasure is often below the roots. Waterlogged soil slows decay, so fallen leaves, branches, and roots do not break down completely. Instead, they accumulate as peat, layer after layer, sometimes for thousands of years. This buried organic matter can store vast amounts of carbon. The forest above may be lush, but the dark ground beneath it is an even larger archive of past growth. When peat swamps are drained, burned, or cleared, that stored carbon can escape rapidly as carbon dioxide and smoke. Fires in dried peat can smolder underground and become extremely difficult to extinguish. These ecosystems show how storage depends on wetness. Keep the ground saturated, and dead plant matter becomes a locked vault. Drain it, and the vault can open. A peat swamp is a forest, a wetland, and a climate memory. Boreal forests circle the north like a vast green belt. Across Canada, Alaska, Scandinavia, and Russia, The boreal forest stretches around the planet in a great northern band. It is dominated by spruce, pine, fir, larch, birch, and aspen, all adapted to short summers and long winters. This forest may look sparse compared with the tropics, but its scale is immense. It shelters wolves, moose, lynx, bears, owls, migrating birds, and countless insects. Much of its carbon is stored not only in trees, but in cold soils where decay is slow. Fire, snow, permafrost, and insects all shape its rhythm. In summer, it can hum with mosquitoes and birdsong. In winter, it becomes a frozen world of needles and silence. The boreal forest is one of Earth's great life zones, a circumpolar wilderness that helps regulate climate far beyond the north. Deciduous trees drop leaves to survive freezing winter conditions. For broad-leaved trees in cold climates, winter leaves would be expensive and risky. Thin leaf surfaces lose water, and frozen soil can make replacement difficult. Ice, snow, and wind can also damage broad foliage. So many species withdraw valuable materials from leaves in autumn, seal off the stems, and let them fall. This is not weakness. It is seasonal strategy. By shedding leaves, the tree reduces water loss and avoids carrying fragile structures through the hardest months. The bare branches may look dormant, but buds are already prepared for spring. Inside them are miniature leaves and flowers, waiting for the right signals. Dropped leaves become litter, then soil, then nutrients for future growth. The annual fall is therefore not an ending. It is conservation, recycling, and preparation. A winter tree is not empty. It is holding its next season in reserve. Evergreen needles are tough leaves built for difficult seasons. Pines, spruces, firs, and many other evergreens keep their foliage through winter because their leaves are built differently. Needles are narrow, waxy, and often protected by thick outer layers that reduce water loss. Their shape helps them tolerate cold, snow, and dry winds. Keeping needles allows the tree to begin photosynthesis quickly whenever conditions improve, even during mild winter days or early spring. This is especially useful where the growing season is short. Needles also tend to be costly to produce, so keeping them for several years can save energy. Their dark green surfaces can absorb low winter light, while their flexibility helps shed snow. An evergreen forest may appear unchanged across the seasons, but each needle is a piece of careful engineering. It is a leaf designed not for softness, but for persistence. Some alpine trees grow twisted by relentless wind and ice. Near mountain tree lines, trees often lose the upright symmetry we expect from forests. They may crouch low, lean away from prevailing winds, or grow into twisted shapes known as krumholtz. Snow can bury lower branches and protect them, while exposed parts are scarred by ice crystals and freezing air. Wind dries buds, breaks shoots, and shapes growth year after year. The result can look almost sculpted, as though the mountain has pressed its weather into wood. These trees may be older than they appear because harsh conditions slow their growth dramatically. A small, gnarled form could represent decades of survival. In such places, height becomes dangerous, and staying low can mean staying alive. Alpine trees remind us that shape is often a biography. Their bent trunks and flagged branches are records of storms endured in place. Bonsai trees are shaped by patience, not genetic dwarfness. A bonsai is not usually a special miniature species. It is a normal tree guided into smallness through careful cultivation. Growers prune branches, trim roots, shape trunks with wire, control soil, and manage water and nutrients over many years. The aim is not simply to make a plant tiny. It is to evoke the feeling, of an old tree in nature, shaped by wind, age, and landscape. A bonsai may be only a few inches tall, yet suggest a mountain pine that has survived centuries. This art depends on biology. The tree must keep growing, healing, and responding to each cut. The grower works with those responses rather than against them. Bonsai reveals something remarkable about trees. Their form is flexible. Given time, attention, and restraint, a living plant can become a landscape in miniature. Tree grafting can join two living plants into one. Grafting is one of humanity's most astonishing botanical skills. A piece of one tree, often a twig with buds, can be attached to another tree's root system. If the tissues align and heal together, they become one functioning plant. The upper part keeps the fruit, flowers, or growth habit of the chosen variety, while the lower part can provide disease resistance, size control, or tolerance for local soil. This technique has shaped orchards for centuries. It allows farmers to preserve a beloved apple, pear, plum, or citrus variety exactly, rather than gambling on unpredictable seeds. The joined tree is a partnership made by human hands and plant healing. Two separate lives are cut, matched, bound, and persuaded to grow as one. Every grafted orchard is full of these living unions, quietly producing familiar fruit from an extraordinary act. Some fruit trees are cloned to preserve exact flavors. Plant an apple seed from your favorite apple, and the tree that grows will almost certainly produce something different. Fruit trees mix genes through pollination, so seeds are experiments, not copies. To preserve a particular flavor, growers clone the tree by grafting or cuttings. That means many fruits with famous names come from living copies of one original plant. A variety prized for sweetness, acidity, texture, fragrance, or storage quality can be carried across centuries by moving pieces of wood from tree to tree. This turns flavor into a lineage. The fruit in a modern orchard may connect back to a chance seedling discovered long ago in a garden, farm, or roadside. Cloning does not make the tree artificial. It uses the plant's natural ability to regrow from living tissue. The result is delicious continuity, passed from branch to branch. The same apple variety can spread through grafted branches. A named apple variety is not a family of similar trees. It is usually one genetic individual multiplied again and again. When growers want that exact apple, they take a twig from an existing tree and graft it onto a new rootstock. If it succeeds, the new tree produces the same variety, because its fruiting wood is genetically the same as the original. This is why a centuries-old apple can still be eaten today, even though the first tree may be long gone. Its identity survives as copied branches growing in new places. Rootstocks may change the tree's height, vigor, and disease resistance, but the fruiting variety remains the same. It is a strange kind of botanical time travel. A flavor discovered by someone generations ago can reappear in your hand because people learned how to move a tree through pieces of itself. Tree resin can trap insects and become amber. When certain ancient trees were wounded, sticky resin flowed out to seal and defend the damaged area. Sometimes insects, spiders, pollen, feathers, or tiny fragments of forest life became trapped in that golden fluid. Over immense stretches of time, buried resin could harden and transform into amber. Unlike ordinary fossils, amber can preserve delicate details with astonishing clarity. A mosquito's legs, a fly's wings, or a mite clinging to a hair may remain visible after millions of years. The resin began as protection, but it became a time capsule. It captured small moments that would normally vanish without trace. Amber does not preserve whole lost worlds, but it preserves glimpses of them with almost impossible intimacy. A drop from a tree can become a window into ancient air, ancient insects, and forests that disappeared long before humans existed. Ancient amber forests preserved tiny worlds in golden detail. Some amber deposits hold entire communities from vanished forests. Inside them, scientists have found ants carrying prey, spiders near silk, flowers, pollen grains, feathers, and insects caught in the middle of everyday life. These are not grand fossils like dinosaur bones. They are small scenes, frozen by accident. Their value lies in detail. Amber can reveal what creatures looked like, what plants were present, and sometimes how organisms interacted. A forest that rotted away completely may still survive in these little golden fragments. Each piece is both beautiful and scientifically precious. It began as resin dripping from bark, then passed through burial, pressure, chemistry, and deep time. To hold amber is to hold a preserved pause. The tree that made it is gone. The forest is gone. Yet a tiny drama from that lost place can still shine in a human hand. Some trees can detect the length of the night. Many trees time their growth, flowering, leaf drop, and dormancy by measuring darkness. The length of the night changes predictably through the year, and plants use light-sensitive pigments to track that rhythm. In temperate regions, this helps trees prepare for winter before the coldest weather arrives. A tree cannot wait until severe freezing begins to shut down tender growth. It must anticipate. By sensing longer nights, it can begin forming protective buds, changing leaf chemistry, or slowing new shoots. This internal calendar is one reason moving plants far from their native latitude can be difficult. Their inherited timing may not match the new pattern of light and darkness. The ability feels almost like awareness of time, though it is built from chemistry. A tree stands in one place, reading the season not by clocks, but by the lengthening shadow of night. Leaves change color when green chlorophyll breaks down. Autumn color begins with disappearance. During the growing season, chlorophyll dominates leaves, making them green as it captures light for photosynthesis. As days shorten and temperatures shift, many deciduous trees stop replacing that green pigment. Once it breaks down, other colors that were hidden can show through. Yellow and orange pigments, called carotenoids, were often present all along. Reds and purples can be made later from sugars trapped in leaves, depending on species and conditions. The result is a seasonal unveiling, not a simple painting on of color. Weather shapes the display too. Bright days, cool nights, and adequate moisture can intensify certain hues. The beauty is tied to withdrawal, as the tree reclaims useful nutrients before letting the leaf fall. Autumn is therefore not just decoration. It is chemistry, conservation, and light revealing what green had concealed. Autumn colors can protect leaves during their final days. The reds and purples of some autumn leaves may do more than delight the eye. These pigments, called anthocyanins, can help protect leaf tissues while the tree withdraws valuable nutrients before leaf fall. As chlorophyll breaks down, leaves become more vulnerable to bright light and oxidative stress. Anthocyanins may act like sunscreen, giving the tree more time to recover nitrogen and other useful materials. This idea is still studied, and not every red leaf has the same explanation. In some species, color may also signal chemical defenses to insects. Whatever the exact mix of causes, the effect is remarkable. A tree nearing seasonal loss invests energy in color that may help manage the transition. What looks like a final flourish can be practical. The leaf is not simply dying beautifully. It is helping the tree prepare for survival. Tree seeds travel by wind, water, animals, and fire. Because trees cannot walk, their seeds must find other ways to leave home. Some ride the wind on wings, plumes, or spinning shapes. Some float down rivers or across seas. Some are swallowed by animals and deposited elsewhere with fertilizer already attached. Others are hidden in caches by birds or mammals, then forgotten. In fire-prone landscapes, some seeds wait in cones or soil until heat opens a chance for new growth. Each method solves the same problem. A seed must escape the shade and hunger surrounding its parent. The variety is astonishing because the stakes are so high. Too close, and the seedling may be smothered. Too far, and it may land where it cannot survive. Tree dispersal is a quiet form of adventure. Every seed is a tiny traveler launched into uncertainty by a rooted life. Maple seeds spin like tiny helicopters as they fall. A maple seed is attached to a papery wing called a samara. When it drops, air pushes against the wing and sets it spinning. This slows the fall and gives the wind more time to carry it away from the parent tree. The motion is so efficient that engineers have studied it for ideas about small flying devices. To a child, it may look like a toy. To the tree, it is a dispersal machine. The seed itself is heavy enough to contain stored food and a tiny future plant, while the wing turns gravity into rotation. When many maples release seeds at once, the air can fill with little spinning journeys. Each one may land on pavement, water, grass, or open soil. Only a few will succeed. But for those few, the helicopter fall is the first movement of a rooted life. Coconut palms can send seeds across open ocean. A coconut is built for travel. Its tough, outer husk cushions the seed, traps air, and helps it float. Seawater may carry it away from the parent palm, sometimes across long distances, until it washes onto a suitable shore. If conditions are right, the seed can sprout near the high tide line and begin a new tree. This ocean-going strategy helped coconut palms spread across tropical coasts and islands, although people also carried them widely because they are so useful. Inside the fruit are water, food reserves, and the embryo of the next palm. The whole structure is a survival capsule designed for salt, sun, impact, and time. Few tree seeds feel so adventurous. A coconut may fall from a palm, enter the surf, drift beyond sight, and arrive somewhere new with enough stored energy to begin a grove. Some pine cones open only after intense heat. In fire-shaped forests, certain pines keep their seeds sealed inside cones for years. The cones are held shut by resin, like tiny vaults waiting for the right disaster. When flames pass through, heat melts the resin and the scales open. Seeds then fall onto ground that has been cleared of thick litter and competing plants. Ash may add nutrients, while sunlight reaches the soil more freely than before. This strategy is called serotiny, and it turns fire from pure destruction into an opportunity for renewal. Lodgepole pines and jack pines are famous examples. Without enough heat, many of their cones may remain closed. It is a remarkable bargain with danger. The tree stores its future in wooden capsules, then releases it when the forest has been opened by flame. Fire can reset forests and awaken buried seeds. After a burn, a forest may look ruined, but beneath the dark surface, many beginnings are waiting. Heat can crack hard seed coats, smoke chemicals can trigger germination, and newly exposed soil can become a perfect nursery. Plants that were shaded for years may suddenly receive sunlight. Minerals locked in old leaves and branches can return to the ground as ash. Some species depend on this disturbance to renew their populations. The first green shoots after fire often belong to plants that were prepared long before the flames arrived. Of course, Fire can also be devastating when it is too frequent, too intense, or driven by drought and human pressure. But in many ecosystems, burning is part of the ancient rhythm. It clears space, changes competition, and begins the forest's next chapter from seeds hidden in the earth. Giant sequoias need small fires to clear their seedbeds. A giant sequoia produces thousands of tiny seeds, but those seeds need the right place to begin. Thick layers of fallen needles and branches can block them from reaching mineral soil. Low-intensity fires help solve this problem. They clear the forest floor, open the canopy, and create patches of bare ground where young sequoias can take root. Fire also helps release seeds from cones and reduces competing vegetation. For centuries, indigenous burning and natural lightning fires helped maintain these conditions. When fires were suppressed for too long, dense fuel built up, and later fires became more dangerous. The sequoia's story is therefore not simply about resisting flame. It is about needing the right kind of flame. The largest trees on Earth begin from seeds so small they can be held on a fingertip, waiting for a cleared patch of sunlit soil. The tallest known tree is a coast redwood called Hyperion. Hidden in a protected California forest, this living giant rises to more than 100 meters. Its exact location is not public, because too much attention could damage the fragile ground around its roots. That secrecy is part of its protection. What makes its height so astonishing is not only the number, but the biological difficulty behind it. Water must travel from soil to crown through an immense column of wood. Leaves at the top must survive wind, sun, and dryness far above the shaded forest floor. The tree grows in a narrow coastal climate where fog helps ease that strain. It is both a champion and a warning. Its greatness depends on the whole forest around it, including soil, moisture, shade, and neighboring trees. A record-breaking tree is never truly alone. It stands because an ecosystem holds it up. General Sherman is the largest known tree by volume. In California's Sequoia National Park stands a tree so massive that height alone cannot explain it. Its trunk contains more living wood than any other known single-stem tree on Earth. It is not the tallest, and it is not the widest, but its total volume is extraordinary. The lower trunk is immense, rising like a column from the mountain forest. Giant sequoias can live for thousands of years, and they keep adding wood throughout their lives. Thick bark helps them survive many fires, while their size gives them resilience against storms and decay. Standing nearby, people often feel the scale before they understand it. This is not a tree that can be taken in all at once. It is a living accumulation of seasons, sunlight, snowmelt, and time, gathered into one enormous body. The Methuselah tree has grown through nearly 5,000 years. Somewhere in California's White Mountains, an ancient bristlecone pine has been alive since deep antiquity. Its precise location is kept hidden, because even admiration can become a danger when too many people come too close. This tree has endured in poor soil, fierce wind, cold, drought, and a short growing season. Those hardships helped shape its longevity. Slow growth creates dense wood, and dry air slows decay. The tree may look partly dead, with twisted bare wood exposed to the sky, but narrow living strips continue to connect roots and needles. It has survived while human civilizations rose, changed, and disappeared. Its age is not a mythic exaggeration. It is measured through the patient science of tree rings. To imagine one living organism holding its place for nearly 5 millennia is to feel time become almost tangible. Some sacred groves protected rare forests for centuries. Around the world, Communities have set aside patches of forest because they were connected to spirits, ancestors, temples, springs, or local traditions. These sacred groves often escaped heavy cutting, even when surrounding landscapes were cleared for farms, fuel, or settlement. As a result, they sometimes preserved old trees, rare plants, medicinal species, and wildlife that vanished elsewhere. Their protection came not from modern conservation law, but from belief, respect, and custom. In parts of India, Africa, Europe, and beyond, sacred groves became living archives of older ecosystems. They show that culture can shape ecology in powerful ways. A story, a taboo, or a ritual boundary can protect more life than a fence. These groves remind us that forests survive not only through biology, but through meaning. What people revere, they may also learn to preserve. Medieval shipbuilders depended on oak for strength and durability. For centuries, oak was one of the great materials of seafaring power. Its wood is strong, hard, and resistant enough to become hulls, ribs, beams, and planks. In medieval and early modern Europe, shipyards needed enormous quantities of carefully grown timber. Curved oak branches were especially valuable because their natural shapes could be fitted into the frames of ships. A single large vessel could require hundreds or even thousands of trees. This demand influenced forests, laws, trade, and naval planning. Trees were not just scenery around villages. They were future fleets, growing slowly across generations. The strength of oak helped carry merchants, explorers, fishers, and armies across dangerous seas. When we imagine old wooden ships, we are also imagining forests transformed by human ambition. The ocean journeys began decades earlier, in acorns, soil, and patient trunks. Charcoal from trees helped fuel early metalworking civilizations. Before coal became dominant, charcoal was one of the essential fuels for turning ore into metal. It burns hotter and cleaner than ordinary wood because it is made by heating wood with limited oxygen, driving off moisture and volatile compounds. Ancient and medieval metalworkers used charcoal to smelt iron, copper, and other metals, helping create tools, weapons, nails, plows, and machinery. Behind every forge was a landscape of trees cut, stacked, and slowly converted in smoking earth-covered pits or kilns. This demand shaped woodlands and sometimes caused serious deforestation near mining and metalworking centers. Yet without charcoal, many early technologies would have been impossible. The strength of the sword, the edge of a tool, and the frame of a bridge could begin with trees turned black by controlled fire. Forest energy helped pull civilization from stone into metal. Paper began as transformed plant fibers pressed into sheets. The story of paper is a story of trees, grasses, bark, rags, and human ingenuity. Early papermakers learned that plant fibers could be soaked, beaten, suspended in water, lifted on screens, pressed, and dried into thin sheets. Later, wood pulp made paper widely available on a vast scale. This changed history. Books, letters, maps, newspapers, scientific notes, legal records, and schoolwork all depended on portable surfaces that could hold language. Paper made ideas easier to copy, store, and send across distance. It also increased demand for forests, which led to both industrial growth and environmental pressure. The page can seem ordinary, but it is a remarkable transformation. A tree or plant becomes fiber. Fiber becomes sheet. Sheet becomes memory. In that form, forests helped carry poetry, law, knowledge, and everyday human thought through time. Trees can record ancient solar storms in their rings. Most tree rings tell stories of climate, but some contain traces of events from space. When powerful bursts of solar particles strike Earth's atmosphere, they can create unusual spikes in radioactive carbon. Trees absorb carbon dioxide during photosynthesis, so that signal can become locked into the wood formed that year. Scientists have found rare global markers in tree rings that point to extreme solar storms in the past. These events matter because a similar storm today could disrupt satellites, power grids, navigation, and communication systems. The astonishing part is that old trees preserve evidence of invisible weather from the sun. A trunk growing quietly on Earth can hold a record of violence 93 million miles away. Its rings become a calendar not only of rain and drought, but of cosmic events that once swept across the planet. Dendrochronology can date wooden buildings with remarkable accuracy. Every tree ring has a width shaped by that year's growing conditions. In the same region, trees often share matching patterns of wide and narrow rings. Scientists can compare those patterns in old beams, living trees, and preserved wood to determine when a tree was cut. This method, called dendrochronology, has dated houses, churches, bridges, ships, musical instruments, and archaeological sites. Sometimes it can identify the exact year and even the season when timber was felled. That level of precision can transform history. A building may turn out older than expected. A shipwreck may be linked to a specific period. A painting panel may reveal whether an artwork could be genuine. The method works because trees keep calendars in their bodies. Human objects made from wood carry those calendars forward, hidden inside rafters, floors, hulls, and frames. Some trees grow faster after nearby competitors are removed. A tree's growth is shaped not only by its own roots and leaves, but by its neighbors. When competing trees are removed by wind, fire, disease, logging, or age, survivors may suddenly gain more light, water, and nutrients. Their rings can widen, showing a release from competition. Foresters and ecologists use this signal to reconstruct past disturbances in woodlands. A tree that spent decades growing slowly in shade may surge when a gap opens above it. The change can be dramatic, like a person finally stepping into sunlight after waiting in a crowded room. This does not mean disturbance is always good, but it shows how dynamic forests are. Growth is a conversation with space. Each tree is constantly responding to who stands nearby, who falls, and how much of the sky becomes available. Light gaps can create sudden nurseries on forest floors. When an old tree falls, it can open a bright hole in the canopy. Sunlight pours down to ground that may have been dim for decades. Seeds already waiting in the soil may germinate. Saplings that were barely surviving in shade may begin to race upward. Vines, shrubs, and fast-growing trees can take advantage of the brief opportunity. These openings are called light gaps, and they help create the uneven, layered structure of many forests. Without them, the canopy might remain too closed for certain species to regenerate. A fallen giant may look like a loss, but it changes the rules for everything below. The forest floor becomes a stage where young plants compete intensely for the new light. In this way, a single crash can begin a burst of renewal that shapes the forest for generations. Tree canopies form layered habitats high above the ground. The upper parts of forests are not just roofs. They are worlds. In tall tropical forests, the canopy may contain branches, leaves, flowers, fruit, trapped soil, pools of water, vines, mosses, insects, birds, frogs, snakes, and mammals. Some animals spend nearly their entire lives there, moving through branches rather than across the ground. Scientists once studied forests mostly from below, but canopy walkways, cranes, ropes, and drones revealed how much life was hidden overhead. Conditions can change sharply with height. The top may be brighter, hotter, windier, and drier than the shaded understory. Different species specialize in different layers. A rainforest is therefore not one flat habitat, but a vertical city. The ground is only the beginning. Above it, stacked levels of life unfold in the leaves, where entire communities live closer to the clouds than the soil. Epiphytes live on trees without stealing their food. In rainforests and cloud forests, many plants grow perched on branches rather than rooted in the ground. These epiphytes include mosses, ferns, bromeliads, and orchids. They use trees for support, but they do not take sugars from them like parasites. Instead, they gather moisture from rain, mist, and humidity. They catch dust, fallen leaves, and tiny particles that collect around their roots. Some bromeliads form little tanks of water where insects, frogs, and microbes can live. This makes a branch into a miniature wetland high above the ground. Epiphytes add weight to their hosts, but they also increase habitat complexity and biodiversity. Their lifestyle is one of balance. They climb without climbing, live high without trunks, and turn the surfaces of trees into gardens. A forest canopy becomes richer because these plants learned how to live in the air. Orchids can spend their lives perched on rainforest branches. Many tropical orchids never touch the forest floor. They anchor themselves to bark and live in the filtered light of the canopy. Their roots are often wrapped in a spongy layer that absorbs water quickly during rain, then helps reduce drying afterward. Some produce spectacular flowers shaped by long relationships with particular pollinators. Others are small and easy to miss, blooming like tiny jewels among moss and leaves. Orchids also depend on fungi during their earliest life stages, because their dust-like seeds contain almost no stored food. A seed must meet the right fungal partner before it can grow. This makes their lives both delicate and brilliantly specialized. Perched on branches, they turn height into opportunity. They avoid the darkness of the forest floor, catch passing moisture, and open flowers in a world suspended between earth and sky. Sloths grow algae that helps them blend into trees. In Central and South American forests, sloths move so slowly that their fur becomes a tiny ecosystem. Grooves in the hairs can host algae, which may give the animal a greenish tint. That color can help it blend with leaves and branches, making it harder for predators to notice. The fur also shelters moths, beetles, and other small organisms that share the sloth's strange, slow world. This relationship connects animal, tree, and microbe in a wonderfully unexpected way. A sloth is not part of a tree, yet it can look almost like a hanging piece of the canopy. Its slow movement, curved claws, and leafy camouflage all suit an arboreal life. The algae in its coat shows how deeply forest organisms can merge with their surroundings. In the canopy, even fur can become habitat. Some trees are pollinated by wind instead of animals. Not every tree needs bright petals, nectar, or visiting creatures. Many species release pollen directly into the air and let the wind carry it. Oaks, birches, pines, spruces, and many grasses use this strategy. Their flowers may be small and easy to overlook because they do not need to attract animals. Instead, they produce enormous amounts of lightweight pollen, increasing the chance that some grains will land on the right female structures. This can be inefficient, but it works well in open or seasonal landscapes where wind moves freely before leaves fully expand. It is also the reason spring air can fill with pollen that affects human allergies. Wind pollination turns the atmosphere into a reproductive pathway. The tree releases a cloud of possibility, trusting moving air to carry life from one branch, one tree, or one forest to another. Every wooden object still carries the architecture of a tree. A table, pencil, violin, door, bookcase, or floorboard may seem far removed from the forest, but its structure still remembers growth. Grain lines follow the old paths of cells that once carried water and supported the trunk. Knots mark places where branches joined. Rings reveal seasons of faster and slower growth. Hardness, scent, color, and pattern all come from the species and conditions that shaped the living tree. Woodworkers read these signs carefully, choosing pieces for strength, beauty, flexibility, or resonance. A violin's tone, a beam's endurance, and a carved bowl's curve all depend on biology that began in sunlight. Even after cutting, drying, shaping, and polishing, wood is not anonymous material. It is organized life. Every wooden object is a transformed tree, and every grain is a quiet record of how that tree once stood. And so, we've wandered through the hidden lives of trees. We've followed their messages through air and soil, traced water rising through trunks without a heartbeat, and seen how forests can shape rain, shelter cities, and hold carbon in their wooden bodies. We've met ancient bristlecone pines, towering redwoods, patient olives, sacred figs, and coastal mangroves standing between land and sea. We've looked beneath the forest floor, where roots and fungi trade in darkness, and above it, where canopies become whole worlds of orchids, insects, birds, and slow-moving sloths. We've seen fire open seedbeds, amber preserve vanished forests, and tree rings record storms from the sun itself. And now, let those thoughts settle like leaves drifting onto still water. There is nothing more to learn for now, nothing to remember. Just the feeling of standing among trees at the edge of evening, as the air cools, the branches soften into shadow, and the forest continues its ancient work without needing to be watched. Let your shoulders loosen. Let your breathing slow. Imagine the steady strength of roots beneath you, holding the earth in place. Imagine the canopy above you, wide and calm, gathering the last light of the day. If you enjoyed this journey, you're welcome to like, subscribe, or leave a thought below. It helps other sleepy souls find their way here too. And if you're still awake, there will be another gentle science journey waiting on the screen, ready whenever you are. But for now, let the forest grow quiet around you. Let the day fall away, branch by branch, leaf by leaf. Sleep well, and good night.